In this section, we're estimating a population proportion. So the previous two sections were on population means, but now we're trying to guess what percentage of the population exhibit a certain characteristic. As long as we meet these assumptions, we can use the following formulas. The first thing is that the data have to come from a simple random sample. The conditions for a binomial distribution are met. Remember, that meant that the individual trials were independent, it was a yes or no response, and they were repeated a fixed number of times. We also have to require that the sample is large enough so that the sample size n times p hat, the sample proportion, is greater than 5, and the sample size times q hat, or the sample size times 1 minus p hat, is also greater than 5. Then we can construct a confidence interval for the true population proportion p by first finding the point estimate. The best guess we can have for the population proportion is what we call p hat. That's the number of individuals that exhibit the characteristic divided by the number in our sample. The textbook uses r, we like to use x as well, where r or x is the number of successes, or the number of individuals in the sample that exhibit the given characteristic, the thing we're looking for. These are the number in the sample that are going to vote Republican. This is the number in the sample that spank their children, the number in the sample that pass statistics. Whatever we're interested in studying, that's the number of those from the sample, so we can make the sample proportion p hat. Then we have to cook up the margin of error. We said the distribution of sample proportions is approximately normal, so we use a z distribution, a critical value of z times the square root of p hat times q hat divided by n. That's a measure of the standard deviation of this distribution, so shouldn't be totally unfamiliar. Where you remember p hat we just defined, and q hat is simply 1 minus p hat, right? The probability of failure. It's a three-step process, remember: point estimate, margin of error, then we take the margin of error from or add it to the point estimate p hat to create an upper bound and a lower bound, or a lower bound and an upper bound. So here's an example: a retirement confidence survey of 1,152 workers, that's a sample size, revealed that 496 had less than 10,000 in savings. That's the number that exhibit the characteristic, which is less than 10,000 in savings. We'd like to make a 90% confidence interval, so the confidence level is 0.90 for the population proportion of those who have, of workers and retirees in the United States that have less than 10,000 in savings. As soon as you see population proportion, you know that this is a z distribution, so we need the critical value of z. For 90%, we can look that up on the table. Here's a z table. We want the summary right down here. 90% level of confidence gives a z value of 1.645. So there are the three steps. First step, find the point estimate. What's the best guess we have for the proportion of people that have less than 10,000 in savings? That is p hat, which is x over n. And in this case, from these numbers, that's 496 out of 1,152. That number is 0.430556, or approximately 0.430. to 3 decimal places. Second thing we have to cook up is the error margin for this given level of confidence. So the critical value of z times the square root of p hat times q hat divided by n. We found the critical value of z as 1.645. P hat, we use 0.430. Q hat is the complement of this, or 1 minus 0.430. This is a lazy way to just do it right there without making an extra calculation. We can do it right in the problem there, as long as you use parentheses properly and divide by the sample size, 1152. Alternatively, if you want, you can cook up Q hat, 1 minus 0.430, and get that number, and then plug that number in right here, or you can do it in line. It's really your choice. The thing you want to do is make sure that you don't make any big giant intermediate rounding mistakes or rounding errors. So if you want to be very confident in this answer, I would cook up this p hat business and use all those decimal places by creating the margin of error 1.645 times the square root of p hat, which I just made. So by using the second minus key, I get all that answer, times 1 minus that answer, and divide all of that by 1152. All of it's under the square root, and having the calculator do the hard part saves me from having to write it all down, but it also minimizes any rounding error. For a margin of error now I have 0.023998270. Of course all those decimal places aren't necessary, but I want you to know how accurate we can be. Then the third step, create the lower and the upper bound. So that's p hat plus or minus the margin of error. We'll make a lower bound when we subtract and an upper bound when we add them. So p hat 0.430 plus 0.023998 yada yada is a point. We could even go back up here and grab that whole answer, subtract this margin of error, and then do it again, but change it to plus. You would like. So I mistakenly wrote a plus here for the lower bound. Make sure that you have minus for the lower bound, of course, and 0.430 plus 0.023998 for the upper bound. And then in the calculator I've done it more accurately, way more decimal places than I wrote down, but it helps me track my numbers. 0.40655572852 and 0.45455386. Probably here we'll round to 3 or 4 decimal places, so if I go to 3, that will round to 0.407 and 0.455. So we can say between 40% and 46% of workers and retirees in the United States have less than $10,000 in savings. 0.407 to 0.455.